All right, so this is AP Physics, see, Mechanics, all right, and these are the 2018, I think, questions. All right, so student wants to determine the value of the acceleration due to gravity for a specific location, sets up the experiment. A solid sphere is held vertically at a distance h, and then it releases the sphere when the electromagnet is off, and then we start a timer. Well, when taking the first data point, the student notices that the electromagnet actually releases the sphere after the timer begins. What would the value of G be greater than, less than, or equal to? All right, so we should be thinking about a kinematics equation here. So which equation should I be thinking about? All right, so I'm going to assume everybody's typing. Change in y is equal to v naught yt plus 1/2 a t squared, right? And so what we want to notice here is that time is actually going to be greater, all right, than we would expect, and therefore your acceleration would be less than. All right, does that make sense? Okay, guys are good? Great. Okay, so then we have, basically we have some data, and we don't necessarily, I think, need to worry about graphing it. We will set it up though, and I'll give you the answer. Oh, I sent you guys. Okay, so course correcting here. This is 2016 exam. All right, on the dot, which represents the cart. All right, so here we have a cart on a track, force sensors, so a spring, and then they tell us we have no friction. So we want to go ahead and write all of the forces on the free body diagram. Cool. All right, so in terms of, and we have to be quantitative about it, all right? So meaning that the longer the area, the greater the force. All right, so we should have mg is the force of gravity. We should have a normal force. And let's see, so from there, all right, we need to have a tension vector. And let's see. All right, so I would have a tension vector because of the string. It's not a spring as I originally thought. And that should be that. Now, if we had, oh, friction is not negligible. Okay, so then friction would be opposite the direction of motion. Okay, any questions so far? All right, and then quantitatively, Fn should be equal to mg, and your force of tension should be greater than the force of friction. All right, great. All right, so I'm gonna minimize this and put up the next part. All right, so there's the data, and we are not going to actually calculate the graph, but I'm gonna draw it for you, or at least like explain it. and then we'll do the rest of the questions. Again, I don't think that you're going to get anything that requires a line of best fit. All right, so if we were to graph it, we're going to get a straight line. All right, we want the, okay, they put the axes on there for us. And I'm going to give you the slope. All right, the slope here is going to be 2.16. All right, and note here that we have F is my Y, and then M is my slope, and then A is my, sorry, this is X, all right, this is Y. All right, so 1 over M is my slope. All right, so if let me just rearrange this. So A is equal to F over M. All right, so this is Y is equal to X and then 1 over M. So this is the, this is going to be 1 over M is my slope, essentially, where M is the mass. All right, that's what I was trying to get at. All right, so our slope is 2.16. And therefore, the mass of the cart is going to be 1 over 2.16. And that should give us 0.46 kilograms. All right, and then if we wanted to determine the force of friction, all right, if I was to extend this line, the intercept is going to be, the x-intercept is going to be the force of friction. All right, is everybody clear on why that is? Fantastic. All right, and then if I was to actually get a number here, it would be 0.27. All right, so I don't think that we're going to get questions like that, but understanding the concept is obviously good. Okay. All right, so I'm going to go ahead and just write the, all right, so my mass we decided was 0.46 kilograms. All right, and then your force of friction is 0.272 newtons. I'm going to erase the graph so I have a little room. All right, if you guys have questions, please make sure you ask them, chime in. All right, so the above experiment is repeated using a constant force sensor reading of 0.46 newtons. Okay, let's hang on for the question. If you, for example, got the mass wrong and used that value for the rest of the problems, would you get penalized more than once? No. They would mark the mass wrong, and then they would mark the rest of the problem correct. All right, provided that you did the rest of the problem correctly using the incorrect mass. Does that make sense? Yeah, no, and that's pretty constant across all of the AP exams. That's not just this one. So the common common advice is to make sure that you write, like, if you can't get an answer, just write it as, you know, X kilograms and then use that X later. Something like that. Okay, so for this problem, we want to determine the acceleration. So we're going to use Newton's law for that. All right, and so sum of forces in the X direction is going to be equal to your force that's applied, so your tension minus the force of friction, all right, is equal to MA. Right, and so our tension, we're told, is 0.45 newtons. We just solved for friction, and we have the mass, so we can pretty easily solve this. So tension minus force of friction is equal to M, 0.45 minus 0.272 over our mass was 0.46, and we get about 0.37 meters per second squared. So this is just Newton's second law. Any questions so far? Okay, so the string breaks at time t equals 2. Calculate the time it takes for the cart to stop after the string breaks. Okay, so now everybody agree that once the tension is gone, the only force that's involved is the force of friction? Does everybody agree with that? So your acceleration is just going to be the force of friction over m, and then because the force of friction is always opposing motion, it's going to be negative. All right, so negative 0.272 over 0.46 is going to be my acceleration. All right, and then I'm going to plug that into VF is equal to V naught plus AT. All right, does that make sense to everybody? Okay, great. All right, so, okay, so now we're not able to actually solve this quite yet, right? We have to actually figure out what your initial velocity is. All right, so I'm gonna figure out my initial velocity using the info that's up here. All right, everybody with me on that? So I don't know what this is. I don't know how fast it's going. I have to figure that out. All right, so I'm gonna use the actual same equation. All right, but this is gonna be before the string breaks. So I'm gonna be solving for my VF here. All right, so initial velocity is 0 because of the from rest. From rest means that my initial velocity is 0. All right, and then I know my acceleration is 0.37, and then t is 2. So therefore, my initial velocity that I get to use to solve the problem is 0.74. Right, so this is right before the string breaks. All right, so then I plug that into up here. All right, I know my final velocity is 0. It's going to come to rest. All right, I know I'm starting with 0.74, and then my acceleration is this thing. All right, and then when I solve for t, I get 1.28 seconds. All right, so kind of a two-part problem there. Does anybody have any questions? Okay. All right. The experiment analysis in parts A and B are repeated with a cart that has the same mass but a greater force of friction. So, what will the slope of the new line be? Does anybody want to chime in? So in the extent, why is it the same? It's the same, but why is it the same? That's right. Because yeah, good. And the force sensor reading is taking into account the force of friction. Okay, will the horizontal intercept of your new line be greater, less, or equal to? So remember that that horizontal intercept was the force of friction, right? So if I have an increased force of friction, then I know that my intercept is going to be greater. Yeah, good job. All right. Does anybody have any questions on that question? Okay, I'm going to move on. All right, so we're going to do as much of this problem as it makes sense to do. All right. So remember that harmonic motion is not on your exam this year, right? And neither is gravitation. So with that said, we're going to do the questions that I think are kind of in the purview, which is essentially, I think you can calculate energy, and I think that you can use Hooke's law. I don't think that we have to worry about, like angular frequency and stuff like that. All right, so we have a block of mass 2m that rests on a horizontal frictionless table. That's helpful. Attached to a relaxed spring. The spring is nonlinear and we have a force. Okay, where b is a positive constant and x is the displacement. And then we have another block of 3m with some initial velocity. And then we want to draw forces here that act on the block before they collide. Okay, so before they collide, we want 2mg, all right, and then we have a normal force, and then I have 3mg and a normal force. All right, and we would specify M1, N1, and N2 there. All right, now I didn't draw a arrow for the force of the spring. Why not? So before they collide, I didn't draw an arrow. It's relaxed. So what does that mean? So if F is equal to negative kx and it's relaxed, x is 0, so therefore force is 0. Okay, perfect. Good job. All right, so that's the layup question of the hour. All right, so we'll go ahead and put up the next little bit of this. And I'll try to make sure I say what I think is in and what is out. I think this question is fairly, I think, reasonable to assume that it's going to be tested. Okay, so we have the two blocks colliding and sticking together. So we have an inelastic collision. Cool. All right, and what we want to do is derive an expression for the speed of the block right after. So we're going to use conservation of momentum. All right, and so remember that momentum is going to be conserved in all cases. All right, so elastic, inelastic collisions, but remember for elastic collisions, you have conservation of kinetic energy, and for inelastic collisions, you do not. All right, so now this one's inelastic, so we don't have the kinetic energy to play with. All right, so what we want to do is figure out your momentum initial, and then we're going to set it equal to momentum final. All right, so I'm going to say, and then remember that momentum is mass times velocity. All right, so in my initial state, I have 2m, and then it's moving at 0. It's not moving. All right, and then my momentum for this guy is going to be 3m, and it's moving at a speed of v naught. Now, I think, let's see, initial speed v naught, I would probably call it negative v naught because it's going to the left. Okay. And then once they stick together, you have 2m plus 3m and then velocity final. All right, so your final velocity is going to be 3m negative 3m v naught over 5m. All right, and then you can drop that out. Okay. Questions? Everybody okay with that? I believe they took the positive and the negative answer. Okay, so that's that. All right, so this question is not as hard as it looks. All we need to do is plug in the kinetic energy. So kinetic energy is 1/2 mv squared. All right, so this is 1/2, and then your m is 5m. And then your velocity is 3/5 v naught squared. All right, and then we can kind of crunch the numbers. So we have 5/2, and then m, and then 9/25 v naught squared. So that is 9/10 m v naught squared. All right. Simplification is not needed. So if you wanted to leave it in this form, perfectly okay to do that. And it's actually probably better to do that. That way you don't make any mistakes and you make the graders work for it. Good question. All right. Okay, so, all right. So for part D, we're going to derive an expression for the maximum distance. Okay, so we can use conservation of energy for this. All right, I think this is still fair game. So conservation of energy means that your change in kinetic energy of your system plus your change in potential energy is 0. Right? We're not losing energy, we're not gaining energy. So your initial kinetic energy is going to be equal to your potential energy final. Everybody okay with that? Okay. So now 9/10 m v naught squared, and then in order to get your potential energy, you're going to integrate your force equation. All right, so I have negative the integral from x1 to x2 of negative bx3, which is what they gave you, and dx. All right, everybody okay with the setup? Yes, no, in the chat box, please. Okay. All right, so then I can drop out those those negatives. All right, and then we can put in our bounds. How do we know the bounds? So they gave you definite bounds that you would start from 0 and you would end at D. All right, so here you were given a definite integral using the bounds that they gave you. It's another good question. All right, so then 1/4 bx to the 4th from 0 to D. So I think that in this case, you sort of have to solve for, I think you do have to solve for D, or at least attempt to solve for D. I don't think you can just leave it like this. All right, so all right, and that would be your distance D. All right, does anybody have any questions on that? Did I answer your bounds question? Okay, great. All right, I'm gonna minimize that to put up the rest of the question. Okay. All right, so for part E here, in which direction is the net force, if any, when the spring is at maximum compression? Okay, so here we have to know that the force of the spring is a restoring force. So at maximum compression, the spring is going to try to be pushing it back towards equilibrium, so the direction is to the right. And then I think that's how you justify your answer. All right, that the force of the spring is a restoring force. All right, you could also say it's equal to negative kx. I think that would work too. Okay, which of the following describes the magnitude of the net force on each of the two blocks when the spring is at maximum compression? Alrighty. So the magnitude is going to be greater on which of the blocks? So let's just think about Newton's law for this one. So they're stuck together, so therefore your acceleration is the same. All right, and then you have F, let's say 2m. is equal to 2m times a number. And then the force on 3m is equal to 3m times the same number. So which of those is greater? So it's going to be greater on 3m because 3m is greater than 2m. All right, and then you just had to say that the acceleration is the same, and then you would have justified your answer. Okay, so this is by Newton's second law. All right, do the two blocks which remain stuck together and attached to the spring exhibit simple harmonic motion after the collision? Okay, so this question is outside the scope of this year's exam. All right, so you would not get a question like that and you would not have to answer it. For part 1, do we need to specifically state that the restoring force is, that the spring force is a restoring force, or could we just describe it? Okay, good question. I think you can just describe it. But if you know that it's a restoring force, why not just say it? You do need to know springs, but you do not need to know simple harmonic motion. So you would not get any oscillator questions. All right, so part F would be outside the scope. The rest of it would be inside the scope. Okay. All right, so the next question is a fun one. No, that's a good question. You don't want to waste your time, obviously, putting together notes for stuff that you know isn't on the exam. So oscillator questions are not going to be on the exam. Okay. All right, any questions before I get started on the last one? Okay, so we have a uniform rod of length D that has one end fixed to the central axis of a frictionless circular platform. We have a radius, and then we have an ideal spring fixed at the other end of it. And okay, so it's going to move along the platform with some radius. All right, it's going to go around in a circle. Equilibrium length of the spring is d over 2. And we have some data that we might need. All right, the motor is going to rotate the plate counterclockwise. And then we have a constant angular speed. No, that's that. So, all right, so for part A, we're going to derive an expression for the spring constant. All right, so for this one, we're going to say that the force of the spring has to equal your centripetal force. All right, and then that would have to equal M and then a MAC. All right. So from here, then we're going to say this is Kx. All right, your force of the spring, and then M, and then now we don't necessarily know your linear velocity or your linear acceleration, so we're going to put that in terms of your angular acceleration. So this should be equal to r and then omega squared, okay? And then from there, what we're going to do is make substitutions for x and r, all right, which I think is pretty self-explanatory. So here x, we're sort of told, is d over 2. And then m and then r looks like it's 2d. And then omega squared, okay? And then we're solving for k. All right, note that the d's would cancel. So k is going to be equal to 4m omega squared. All right, that's not super easy. Definitely not easy. All right, any questions on that question? Great question. Okay, so what are the units for a spring constant? So if F is equal to negative kx, this is newtons, this is meters. So in order to make the two sides equal to each other, this is newtons per meter. Okay, determine an expression for the rotational inertia of the block. Okay, so by definition, I is going to be equal to the sum of your mr squared. And from there, we just make a substitution. So this is 4md squared. Okay, any questions on that one? All right, so then for 2, we need to figure out your moment of inertia for the whole thing. All right, and so that is going to equal the platform, the rod, and the object. So IP plus IR plus IO. All right, and so for the platform, they gave it to us. And they gave us the rod. All right, so MR. And we just solved for the object. Okay, and let's see. So that's that. So then we want to get this into, something that remotely looks reasonable. All right, so I think that you could stop here, but you might want to take it one step further to put in the 2d squared. All right, so I'm going to go ahead and try and clean this up a little bit. Okay, so I think at that point you would be fine to leave it. But then again, we can clean this up a little bit if we want to. All right, I didn't mean to do that. So they gave us the masses, so it seems fitting to use them. This is 5m from here, and then this is 3m. And then if we simplify and we calculate, we end up getting 15md squared. All right, but again, on this year's and in any AP exam, you can just leave them unsimplified, okay? Does anybody have any questions on that? Okay, so I'm going to just write these up here. Okay. Any questions before I erase? Everybody doing okay? Yes, no, maybe? All right, so for determine expression for angular momentum, all right, so by definition, I omega, all right, and we just solved for I, so we just plug it in. All right, and then again, this is a situation where if you didn't get the previous one correct, you would just make up a number and put it in. Okay. All right, any questions? I'm gonna put up the last couple parts. All right, I'm gonna put this up here. All right. Sorry, it's a little small. All right, so for part D, if you can read it, it says derive an expression for the distance x that the spring is stretched when the rod reaches the position shown in figure 3. All right, so we're gonna do this similar to, what we did before, all right, where we said that kx is equal to mr omega squared. All right, but now we want to make a substitution, all right, for k. So we have 4m omega squared x is equal to m, and then what is my r? So if I look at the figure, it looks like it would just be d plus x. All right, so d plus x, and then omega squared. All right, and then we're going to see a lot of variables drop out here. So I got 4x is equal to d plus x. So 3x is equal to d, so x is d over 3. All right, so that's not terrible. All right, part E is the angular momentum of the entire system increasing, decreasing, or staying the same. Okay, so, all right, so let's see. The answer is decreasing. And then if we want to justify that, we know that the rotational inertia is decreasing throughout the motion, all right? But the angular velocity is staying the same, all right? So angular momentum is I omega, and since that is going down, all right, L is going down. So I decreases, therefore L decreases. All right, does anyone have any questions on that? Okay, in order to keep the system rotating at a constant angular speed, is the motor doing positive work, negative work, or no work? All right, so here your angular speed is constant. Therefore, your rotational inertia decreases. Therefore, your kinetic energy of rotation is decreasing. All right, and then if we think of work as equal to change in energy, if this is decreasing, then this must be negative. All right, that's the work energy theorem. All right, and then we have just one part left. I is decreasing because the radius is decreasing or because the length of the rod. The total length is decreasing. So the motor acts as a pivot. If the pivot is the hinge, how would it apply a torque if it's not at a distance away from the hinge? I'm not sure I understand the question. All right, while you rephrase the question, how does it apply a torque? So R is only 0 at 1 point, right? Well, 2 points. And I think that we're talking about through the entire motion. Okay. All right, and then the last part, we just need to basically draw an arrow that shows the direction of the force. Okay, the acceleration. Okay, so all right, so does anybody have any idea how we would do this? What makes the length decrease? Your distance is decreasing? Okay, so last question. All right, what is the direction of the acceleration? So if this thing is moving to that way, all right, what would my acceleration vector look like? All right, so acceleration is going to be opposite motion, and we're going to be going towards the center of the circle. So we would get something like this, all right, if it's moving like that. All right, and you could have drawn that at any sort of angle that's reasonable. All right, remember that the centripetal acceleration is always towards the inside, all right, to keep the block moving in a circle.